All right, everyone, one more 20-minute sprint, and then you get to listen to me drone on to end the whole shebang today. But before that happens, I can't wait to introduce Eric Davis from Galois. He'll march you through this last of the force protection sessions, and we'll see you on the flip side. In the meantime, please recognize everyone, there is no accommodation for questions and answers during this session. Instead, Eric will get a report of everyone who's attended this session, and he'll be able to reach out to you independently after the event. So with that, thanks for your time and attention today. Eric, the stage is yours for 20 minutes.
Thanks, Dave. And on the question side too, we're open to anyone reaching out and contacting us, whether you're just interested in some of what we're saying here, if you'd like a demo of what we've presented here today or additional information. My email is both on the first slide and then on the final slide of this presentation. So today, I want to talk to you about some of the work we're doing at Galois. But for folks who don't know us, we're an advanced computer science research and development company. We're headquartered in Portland, Oregon, but we have offices in Dayton, Ohio, and Arlington, Virginia. And where we work primarily is on trustworthiness in critical systems. We do this primarily in primary research and development. We do work with the Department of Energy, DARPA, NASA, the DHS, AFRL, NIST, Amazon, and a number of other folks. We've been around for over 20 years by now, have over 100 employees, but we're still a fairly small lab that focuses a lot on these primary research and development areas. A lot of us are former academics, so we care deeply about the science, as well as the connection of these to critical problems and research areas. For me, my research and the research that our lab conducts is around trustworthy AI, ML, and data science, reasoning about complex systems, data-driven science and decision-making, human-machine symbiotic intelligence, and real-time crisis decision-making. Today, I want to talk about real-time crisis decision-making in several different facets as it relates to joint force protection. I think we all know the ideal of this situation. We had all these grand ideas, I think, a few years ago that during a crisis, domain experts would be capable of agile performance with high confidence modeling in response to crisis, and leverage AI and ML and data science to make decisions on actions, policy, with continuous improvements and feedback to improve these outcomes. What we've found out in COVID-19 and numerous other crises in decision-making is the reality is nowhere near this. When we're looking at complex crises, this usually requires large teams of modelers, mathematicians, software engineers, domain experts, decision makers, and the results of this are often not reusable, not maintainable, very difficult to develop, and very often not performable or even correct. And oftentimes we can't even get guarantees on this. And we believe a lot of this comes from the fact that a lot of our AI and ML tech hasn't been built with trustworthiness in mind or even human use in mind. Most of it's been designed for these quick and dirty kind of ad tech deployments where accuracy was not important compared to getting relatively more accurate than what we had before, which was not knowing much at all. So one of the ways that we're looking at enhancing our ability to use these models and to use AI and ML during crisis revolves around several different enhancements to current AI technologies. And one of the ones I'm talking about first is our ability to move the results and to engage with the assumptions and understanding and knowledge of subject matter experts and decision makers. So the goal here is to try to revolutionize the process of analysis, of planning, and mission kind of debriefing by taking the different types of artifacts that are now separate, which could include human artifacts like papers, documentations, and studies, mathematical artifacts like formal specifications, models, or statistical data, and executable artifacts, specifically code or software, and their visualizations, and building them into a platform that more easily connects these artifacts by more than just human labor. One of the real reasons we want to do this is by connecting these knowledge layers or representations, we can ensure that it's not just the software engineers that can change the models. It's not just the mathematicians who can question whether a term or an assumption is right, but it improves the ability of the decision makers themselves to engage in the artifacts by moving them to different representations that most closely match the needs and the capabilities of their users. So for a lot of these artifacts, it's meant raising visual artifacts and models into graph-like formalisms that allow SMEs and decision makers to understand how we're reasoning about things, what different data is being used in different areas, and improving their response times by having AI do the hard work of translation. This makes sure that we can get the translation correctly and also rapidly between these different representations, as well as automatic re-implementation to avoid issues of being locked into legacy solutions, libraries, or code. An example of where we've applied this in practice is most recently with the COVID-19 crisis. So we did a lot of work with the CDC and the NIH through DARPA. And as everyone knows, the CDC forecast for any one individual model was pretty bad. The performance wasn't great. It didn't match realities. And the models that we actually did have predicted a whole set of different possible futures. And there was very little model agreement. This created a real crisis within the crisis of even understanding what models were credible, what models were fit for the purpose of certain analysis tasks. Oftentimes these models weren't individually incredible. It was just that they were designed for one specific purpose, or their hyperparameters were so finely tuned that they weren't generalizable. So the question we were addressing here with the NIH and CDC was, how can we build robust measures of trust when there's so much disagreement? How do we automatically assess model credibility? And bringing them into our tools was one way that we helped to understand this problem. Looking at a specific set of case studies here, this is an example of a specific model we were asked to look at. It was a fairly popular model, got popularized by the New York Times, and overall is a fairly accurate epidemic model. When we looked at the actual results plotted by the model, they matched our expectations, but when we took the actual documented equations underlying those models, what we found was a translation error. The code itself, which was thousands of lines, had the correct set of assumptions and equations, but the equations as documented in the background for the model and in the papers were incorrect. Now, normally this would be a very laborious process of walking through the model, examining the code, examining the human artifacts, translating between them and looking for discrepancies, and then finally re-implementing the various models. With our tools that we were able to apply to this with DARPA and the CDC, we were able actually to extract the models, synthesize new executables from the equations directly, and in less than a minute find and correct the error that was present in the human documentation while validating the results from the actual software. Similarly, when we went back and studied some of the double epidemic models to help validate certain hypotheses that were going around at the time, we looked at a paper that had been around for about 11 years. This was on the original SARS-CoV-1 epidemic. It was very influential in developing some of the policy and initial models of COVID-19. But when we went back to the original paper and extracted models from the equations that were given, we again found we couldn't reproduce the results printed in the paper. And by this time, the software was long gone and inaccessible. It had bit rotted and been removed even from public revision control. But again, we were able to take these models and the equations and synthesize them into executable artifacts. This technology gives us the ability to translate across these representations with confidence in the correctness of our solution with respect to the original specification. So we're treating these things like the mathematical descriptions or the diagrammatic descriptions as an attempt to give a functional representation. And using this, we were again able to find and correct those errors. In this case, it wasn't an error in the actual model itself, but in the hyperparameterization that was printed in the paper, and then build a credible model from that within minutes that we could then deploy with confidence. One of the takeaways we've learned from this is it's not just about the representations of the models, but preserving a lot of the human representations that form the common ground between different human performers and the humans and machines. We've extended ontology logs in these cases to build kind of a set of human knowledge representations that we can connect to the computational elements, the statistical elements that our models are producing, so that we can label them with human understandable terms. This enables us to establish calibrated trust with the user, where we can surface the outcomes of these models and of these AI and ML systems instead of just as raw statistical data and output, as a set of hypotheses and supporting evidence in more human understandable terms. This allows us to create systems where humans can actually understand why they should or shouldn't trust those reasonings. So instead of it being behind a black box and giving you some random scores, you can actually go through and look at what the evidence is and whether you think it's sufficient for your cases. So trust is not extended when the AI is untrustworthy and not withheld when it is trustworthy. So we can move beyond these initial biases. One of the other consequences of using these ontology logs to characterize the human knowledge is we found that a lot of these human qualitative terms are actually more computational than we thought. So in this case, we're showing the synthesis of new knowledge. So we have the knowledge that there are aircraft and that aircraft have a maximum speed. And in this model, we have a specific aircraft, which is a rotorcraft in the subset light helicopter and is specifically an R-44. While we don't have a specific knowledge artifact for the specialization of maximum speed of an aircraft to an R-44, we can automatically synthesize this with the mathematical underpinnings of these ontology logs by using applied category theory. And it allows our system to reason in human terms that there is a max speed that applies to an R-44 only and defines the performance characteristics of this object in the modeling system. This kind of gets us to the next idea, which is once we have models of individual processes that could be useful during crisis, how do we compose that knowledge during crisis? And this comes into another part of the representational issue, which is that everyone has different ways they like to interact with knowledge. Everyone has different assumptions, and oftentimes these assumptions and representations aren't compatible. So part of what we've done too is extended the ability for teams to work together in confidence. Whenever we look at a joint force protection scenario, we're going to be pulling together a number of different subject matter experts from different areas and trying to compose knowledge artifacts that they've created, often in isolation of each other, that may or may not work with each other. By labeling these in these ontology fashions, we can actually find ways to fuse them together to compositional models that can actually evolve over time. By turning these individual modeling components into something that looks more operatic or as a common building block with known inputs and outputs, during planning, feasibility studies, or other exercises, we can actually reconfigure these models on the fly and look for sources of different information that could fill in gaps in the current modeling process. If we look at current pipelines, we often see a bespoke process of multiple executables that have complicated kind of configurations, a lot of different files and data sets they're looking for, and they can be composed in certain ways that we hope builds a synthesized model across these domain areas. But teaching everyone these individual bespoke components is difficult, and also filling in a lot of the domain expertise that is required on these models can be time-consuming or overwhelming. When we were looking at some topographic flow models, for instance, we saw over 10,000 variables that had to be set by the individual working with the models. By moving these into containerized fashions and abstracting them, we can actually make versions of these models that aren't just represented in ways that help the user understand them, but whose controls and inputs have been simplified and abstracted in ways that cause them to be more usable for one subject matter expert or domain in general. We can alter these representations so that while one user might want a dial that selects between different maps to apply a certain planning tool to, another one may be able to load in full maps if they know that format and can deliver it with confidence. By building these sorts of encapsulations and abstractions, we can build systems that have the same core model that produces these results, but we can specialize them for different user classes to enable their use in also different levels of fidelity. The core models are the same, the outputs can be different, the inputs can be different, and what's packaged with them and their simplicity can be changed on the fly automatically by our AI synthesis tool. We've applied this in several different cases for cooperative compositional modeling to enable explainability, traceability, introspection on results, and reliable governable outputs. This allows us to control the way the models are composed, to control the sets of assumptions they're compatible with, and expose all of these compatibility issues in a way that's reasonable, we can reason about with automated reasoning. We've used this both for fusing across different domains. So for example, this is an analysis we conducted as part of an exercise in modeling ocean currents, wind patterns, and mesoscale couplings, where we were able to take a set of climate models, Navy models of currents, wind models, and turbulence float models to predict the positions of sensors, persons overboard, or other objects floating in this space with higher confidence. We've also applied these techniques when looking at the Ethiopia Oromia region. We conducted a study there with their government, the US government, to try to understand hydrology, agronomy, and geopolitical human movement as it impacted food insecurity and conflict. We were able to build pipelines in this case that dictated what their requirements were and help the individuals at the Ethiopian government work with scientists from different universities and compose models that were developed independently across the globe to form a confident source of reasoning they were able to use to build projections of different levels of fidelity. And furthermore, we allow them to explore the auto-completion of these designs. Sometimes you don't know what's missing from the model, and when you're conducting your analysis, you need something else that provides additional data or additional resolution on a certain quantitative property. We can actually look at those properties by their ontological inputs and reason about how to autocomplete them from the models that exist within accessible databases of these models. Not only can we talk about their compatibility, but we can look at the correctness, confidence, and fitness for purpose for those exact use cases. We've actually built a number of component search tools for another case study where we were working on UUV and UAV design, where we're able to go through and reason about the direct compatibility of different, in this case, motors and propellers and battery systems to understand if the composition would even be correct or if this feasible solution could even be constructed. Another issue I want to go into details on here when it comes to working with models during crisis decision making is speeding up how fast or how long it takes to do this analysis. Part of this is just to allow for initial exploration. In joint force protection studies, we typically begin with a feasibility study and preliminary analysis to even explore the possible solution spaces. Over time, the needs of our models, fidelity, believability, accuracy, and alignment to mission goals increases. But it can be expensive and difficult to compose this with high fidelity models and allocate lots of compute time just to understand if a model is fit for the purpose that we're exploring. We've worked a lot then on model extraction and model reduction. These are ways that we can take a look at a mechanistic model that is often large, describing an entire system, and then reduce it to just the part that solves our particular problem. The methods we have are both exact in this case, where we go through and do a dependence analysis of the underlying mathematics, which result in speedups. In this case, this was a relatively small model, so only 1.4x. But when we look at a larger model like the RASH machine, which is a larger biochemical system, very prominent in cancer discovery, we're able to reduce that down to about 8.4% of its variables and 2% of the events, and maintain executability of the resulting model with 44x speed up in a single execution or 112x when doing hyperparameter searches. When we need speedups that don't necessarily need this exact correctness proof, we've also been looking into surrogate models such as deep Koopman models. These are ways of giving nonlinear dynamical systems data-driven analysis by encoding the dynamics in a linear space and learn an evolution rule to predict interpolated and extrapolated dynamics. We've actually built these in a compositional manner, which is a first for deep Koopman surrogates, where individual models can be composed together using the same systems we were just talking about and trained for individual components. And we find that these all have less than 10% error and run almost instantaneously as they can be solved exactly. We've also found that these models are relatively robust in the design space, so that even though they're trained over a set of known components, the surrogates perform robustly in the corners of the design space since they're learning the actual underlying dynamics. Unlike most models, these don't result in a black box model with no understanding, but a rough kind of characterization of the underlying mathematics. We've applied these beyond just the design problem spaces that I've talked about, also with NASA and the designs of heat shields and representing the physical dynamics of reentry. And in human machine teaming for cyber physical design and looking through very large design spaces for UAV and UUV systems that satisfy certain mission goals. While this covers a lot of the current work that I think is most relevant to the joint force protection, I did want to cover very quickly some of the other work we're doing. We are doing a lot of modeling of human co-performers. We found that while humans think that we're very hard to predict, we're actually surprisingly predictable, especially in domain performance. Individual models can be created of users that allow us to anticipate and fill the needs in terms of resources or planning that a human can encounter. And we can also extend a lot of these ideas to machine-assisted ingestion of large-scale, uncleaned and unstandardized intelligence products to bring models into situations where they can be used directly by their human performers for these cases. We've also done some work in wearability for human health dynamics, intelligent data constraints to encode properties that the FDA and USDA found important for nutrition tracking, and exploring and uncovering evidence of bias within these models automatically to build understanding of the underlying trustworthiness. The last bit I wanted to talk about too is we're also engaged in education as well. I'm a former faculty member and we ran our first summer school last year. I don't believe we're running one this year, but look in the future for workforce training and management solutions where we're pushing out free coursework on trustworthy machine learning and data science. So thank you everyone for your attention. Again, my name is Eric Davis. My email is ewd@galois.com. Feel free to contact us for additional discussions or to arrange a demo of any of this technology or other things that you might be interested in from our portfolios. Thank you very much.
Eric, and thank you so much. That was like spot on for timing. Appreciate it. Appreciated also the information. I don't know about anyone else, but I'm going to walk away a whole lot more aware, if not smarter, about a ton of stuff in the force protection realm today. So thanks for that. As mentioned at the top of Eric's session, he will be able to reach out to all of you who attended his particular presentation today. So look for that after the event. In the meantime, we are 4 minutes away from a couple closing remarks that I have for everybody. Appreciate your time all afternoon today, and we'll see you in 4 minutes on the main stage. Thanks again, Eric.
Thank you.